Good afternoon, this is Schweitzer, and we are looking to do a quick little video here on we know that H plus ions are in fact causing things to be acidic, but how do you actually make an H plus ion? So how do chemical reactions make this H3O plus ion? The first thing we're looking at here again is okay, what is this? The main reaction for acids. Now, acids only cause things via what's called hydrolysis. So what is hydrolysis? So hydrolysis is when an acid, essentially, this is really threw people off a little bit. Some of our original scientists, Arrhenius is one of the guys named, he saw this and he said, okay, I think that an acid, and people were throwing out all sorts of ideas of what makes something acidic for decades prior to this. But they knew acids existed, they just didn't know why. They thought, so Arrhenius is the first guy who said, okay, I think an acid really is just an H plus ion. And therefore something that's an acid should contain an H plus ion. Okay. So that worked out quite well and it really correlated nicely. Eventually they realized that really the acid is just going to be donating to water. So we've changed our definition a little bit to being something that's H plus ion, so really it's something that is an H3O plus ion. And with that being said, these two are now interchangeable. Okay, and we've even gone farther to say that, okay, well, an acid might be really just be an H plus donor. Now, more specifically, on Earth, with all the water, donating to water is like super common. But it could be possible that water wasn't involved, and it was just the fact that it's an H plus donor. Okay, so this is something that we could maybe talk about towards the end of the video. Here's an example of what we have here. Water, this bond right here is severed. So the strength of that bond is really helping or hurting this process. We'll talk about that as well, but therefore it gives us H3O plus ion, which is the hydronium ion. And we have our anion. This just looks like this. HX plus H2O yields, I got a backward forward arrow there, but you can ignore that, H3O plus X negative. Okay? This is called hydrolysis. Very common reaction. It's common because every single acid that has the ability to be acidic does this reaction. They just simply swap out a different anion because that make a different acid. Okay, so let's try it out. Let's write a few of these out. Take a moment, pause the video, and let's write these out. Okay, plus water yields H3O plus Cl minus plus H2O yields H3O plus F negative plus H2O yields, now this is my whole anion, C2H3O2 negative plus H3O plus. Okay. So here we go. So ammonium, this is ammonium. Okay. Ammonium is a cation, so a lot of times ammonium comes with an anion. Let's say, for example, NH4Cl. This would be called ammonium chloride. But when it dissolves, it just breaks apart into chloride ions and ammonium ions. So it's just like that chloride just along to the right. But it says, and then the ammonium can then undergo hydrolysis. Let's sketch out the reaction. Okay. Now we've already gone through some equilibrium rates, so we want to kind of talk about that a little bit here. But this is going to be NH4 plus, this is an acid. So it's going to donate H plus to water, plus water will yield NH3, that's what's left over, plus H3O plus. Okay, write out the equation, did that, sketch the model. Okay, now this is going to be a very much reactant favored. Okay, so we could just starting to figure some of this stuff out here. So I got a beaker, and I'm going to draw pretty much all reactant here. So I'm going to go NH4 plus. I'm not going to draw the water because the whole beaker's water. And then I'm going to draw out some products. We'll give a different color. NH3 and H3O plus. Okay. So, and we could draw more of our reactants if we wanted to, if we want to emphasize that it's reactant favored, which, of course, you're just starting to see what some of this stuff is looking like. So, all right. Perchloric acid goes to completion. Now, this is a different version. So this one here is an equilibrium system, more reactant favored. Now we're going to go to completion. Okay. So in this case, perchloric acid is HClO4 goes to H. Now, sometimes people don't draw the water in here. Okay. They assume that you realize that it's full of water. H3O plus ClO4 minus 1. So that's another way to kind of write the same thing. And therefore, let's draw that out. Now, because it goes to completion, means there's no reactant left. So it's just going to be H3O plus and ClO4 minus. And the more you drew, the more concentrated it would just be getting. Draw a picture to the right did that. Interesting. Okay, good. Next one. So how do metals, how do hydroxide get formed? All right, so hydroxide ions are everything that is a base, okay? But eventually all bases need to have hydroxides. So just a quick overview, Arrhenius, same guy, thought, okay, H pluses are the acids, bases are the hydroxides, which is true. So he thought everything has to have hydroxide. Real simple, we'd have like a NaOH, this common name would be lye. You could buy it at Fleet Farm. And would form Na plus and OH negative. I think people knew what things were basic, so all of a sudden we have this works great, except along comes a chemical called ammonium. Sorry, ammonia. Ammonia. That always was difficult for me. Which one's ammonia, which one's ammonium? Okay, that's this thing, this chemical describe or display all the attributes of a base, but did not contain the NH3. And that really threw people off. If this is base, how is this basic? Well, this thing does produce a base, so it has to produce this, but it does it via chemical reaction, which we've already talked about is hydrolysis. So let's take a moment and look at that. So bases have two ways to produce this. Here we go. So we have our base. Now I'm going to draw as X negative. You could also draw it as NH3. So we know the hydroxides, in this case, are water, are bases. So what's going to happen here is that when it reacts with water, the base is going to accept an H+. Accept. In that way, it turns into OOHX. So this guy, H+ goes this way, producing that guy, and then the water becomes this. So in the end, we thought, well, we know that the base is always accepting an H on water on Earth, but is really the water absolutely needed? Could a base really just be an H+ acceptor? Is that possible? That if we got out of the realm of just water, could it be in other chemical reactions just an H+ acceptor? And that is ending up being one of our main, ideas here. But being in a water systems is super common, and therefore this is just very common. What would this look like? It would be like HX negative plus water would yield HX plus OH negative, and this is the hydrolysis equation. All right, so let's take a moment and write out this guy. Ammonia plus H2O yields NH4 plus OH negative. This is H2O yields HF plus OH negative. All right, ammonia. Again, very common, so we'll do it again. Now, ammonia is something that is very much an equilibrium system. So it's going to be not going to completion. Okay, so we might draw more reactants. All right, so then this guy here is going to be written more as a reactant favored system. Reactant favored. So I'm going to just, that's not this. Okay, so draw a beaker, more reactants and products, goes back and forth. And H3, probably not going to draw any water, so the whole thing is water. Draw a few of those. And then we will draw an NH4 plus and an OH negative. Keep in mind, this is the thing that actually makes a base. Potassium hydroxide goes to completion. So this is your dissolving one. KOH goes to K plus OH negative, which we just briefly talked about initially. This is just going to talk about K plus OH negative, K plus OH negative. Did that one. Okay, next up we got, okay, right, what is an acid-base conjugate pair? So vinegar is a common acid. That's this guy right here. We call it acetic acid or vinegar, but acetate is also a common base. How are these related? Look at, they look almost identical, except it's missing the H plus. Let's write out the hydrolysis equation. Plus H2O, and then goes to H3O plus C2H3O2 negative. This guy is plus H2O yields HC2H3O2 negative plus OH negative. Now, again, on this thing, we want to label our acid-base conjugate pairs. What does that mean? Well, this guy and this guy are the same. Like as in, they're the same substance. So this is the same as that guy. This guy has the H, so we call it the acid. And as we mentioned, acids are going to be proton donors, H plus donors. H plus is just a proton. H plus. And that gives you these results. So this is my base, which is the acceptor. Okay. So again, acids are H plus donors, and a base is an H plus acceptor. Okay. And now the acid on the other side has now lost the H, so now it's just going to call this the conjugate. Now conjugate is a term just for the guy on the other side. Same chemical, base, but because it doesn't have the H anymore, it's no longer an acid, but now it has the ability to accept it, so it's a base. So it flips from acid to base. This is therefore my conjugate acid. Here, conjugate's easy to match up. This guy here, look before and after. Snapshot before, snapshot after. This guy looks like now it's gaining an H. So the water is the donator here. This is therefore my acid. This is my base. This is therefore my conjugate acid, and this is my conjugate base. Okay. Let's take a little closer look at this dissolving process. Right off the dissolving equations. Okay, so this is going to be Na plus OH negative, K plus OH negative. Okay, plus, and I could put plus water if I wanted to. Okay, iron 2 plus 2 OH negatives. What determines how strong or how much we actually get? And that is actually solubility. Okay, this two here are very soluble, so we get lots of these guys. And we call that a strong base. I'll highlight that a little more in a second, but this guy is very little soluble. It's little. So no matter what, we end up having a situation where it just doesn't dissolve well. So in this case, we could have a solution of iron, where iron hydroxide, where that stuff is sitting on the bottom, and it would be even, saturated, yet there's just very little hydroxides in solution. There's some, but just not very much. So a strong base is really a metal hydroxide that is very soluble. And the ones that are really soluble come out of the periodic table, the metals, really in the first two families of the periodic table. Okay, the most common ones likely are potassium and sodium. Okay, those are right here and right here, super common. And that is the end of our video. Thank you very much.